What's up, everyone? Back again with another Tesla mechanical design engineer interview question solved. Before we get into it, a joke. What do you call a criminal driving a Tesla? Stick around to the end of the video for the answer. Alright, in this problem, a solid core, pure copper wire of diameter d, resistivity ρ, and very long length L conducts current I. There is airflow with constant environmental properties shown in the figure. What is the surface temperature of the wire, T sub S? We're going to break this problem down into 3 steps. We don't really need to draw a diagram. So for step 1, we're going to gather the relevant information that's presented in the problem. Step 2, we're going to identify the equations based on that information and then solve our unknowns. And lastly, step 3 is going to be to go back, review the problem, and make sure we're answering in the appropriate way. Okay, now that we know our 3 steps that we're going to take to solve the problem, we can go ahead and jump in with 1, gathering the relevant information. The problem tells us that the wire diameter is denoted by D, resistivity, ρ, and our very long length, L. There's also current denoted by I. These are the terms that we're going to use to find the internal energy generated in our circuit, or in our copper wire. Our convection terms are T infinity, H, which is our thermal conductivity, and T sub S is the temperature at the surface of the wire. So this is pretty much all the information that's given, and we can use this to identify the equations and solve our unknowns. First off, we know that there's internal energy generated from our copper wire and the current running through it. So if you look up energy from current equations, you're going to find that your heating per time is equal to current squared times resistance. And if you look up resistivity, you're going to find that resistivity is equal to resistance times area over length. Solving for resistance, you get that resistance equals resistivity times length over cross-sectional area. You can plug that into your heating per time equation and find that our internal energy generation heating per time is equal to current squared times resistivity times length over pi r squared, which is our cross-sectional area. Now we need our convection equation. Heating per time for convection is equal to our thermal conductivity times area times our change in temperature. This is equal to thermal conductivity times 2 pi r, which is our area of the surface that's exposed to convective heating, times the surface temperature minus temperature at infinity. And the last equation that we're going to need is our energy balance equation. For this, the energy in minus the energy out plus the energy generated is going to be equal to 0 because this is a steady state problem, or the energy conditions are constant with respect to time. So now we know that there's no energy in. The only energy that we have in this circuit is energy out due to the convective heating and the internal energy generated from the current. So we can set our energy generated equal to our energy out, and we can set our equations. Current squared times resistivity times length over area is equal to 2 pi times thermal conductivity times our radius times our surface temperature minus our temperature at infinity. And I accidentally put a big R, but that would be resistance. We should have little r here for radius. So if we solve for our surface temperature, we see that it's just equal to our temperature at infinity plus our current squared times resistivity times length over 2 pi squared times our radius cubed over h. We go back, review the problem, and find that that's what's being asked. So there you have it. As for our joke of the day, what do you call a criminal driving a Tesla? A jewel thief. Let me know if you have any questions or comments, or if you approach this problem in a different way. Leave a comment below. Hope you enjoy.